I'm super excited about this panel. We're going to talk about fully homomorphic encryption, otherwise known as FHE. This is our second team named Phenix today on stage. Not a coincidence. But excited to jump into all this stuff. We just published a blog post a couple days ago. Hopefully y'all read it as part of your homework. With that, let's jump in, guys. Pascal and Guy, thank you for being here. Can you start off by please sharing your respective backgrounds? How did you get into all this stuff?
Okay.
Go ahead.
Okay. I am Pascal. I'm basically a cryptographer, entrepreneur, and I've been working on homomorphic encryption pretty much all my life. I started working on it in the late 90s during my PhD, and I have been working on it ever since. And it's fantastic to see how much this particular field has evolved over time. And it's super exciting to be able to create a company that actually makes it happen for everyone to embrace this technology.
Yeah. So first of all, thanks for inviting us. Guy Itzhaki, I'm the CEO of Fhenix. I've been in this space for many years. My background is I'm doing a lot of cybersecurity activities at Intel. And around 2017, I got into blockchain, built the first permissioned blockchain for the Tel Aviv Stock Exchange. I was leading then confidential compute activities, and it was very obvious, even in 2017, that we have a big problem around data confidentiality in the blockchain space. Homomorphic encryption wasn't mature yet. It was quite complex, but I kept on tracking the progress around that with the work that Pascal and team has done. And then early this year, we started Phenix, which is the first blockchain to introduce native encryption to the blockchain, powered by fully homomorphic encryption.
Thank you all for those intros. And Pascal, can you share a little bit about Zama? How old is the company? What does Zama do?
So Zama was created almost 4 years ago. So I co-founded it with my co-founder, Brandon Indy, who was, at the time, he was selling his previous company that got acquired by Sonos. And at some point, I've been knowing Rand for a few years, and I was working on, in my previous company, Crypto Experts. I was working on homomorphic encryption. And I got this result. And so I reached out to him saying, I think this deserves to become a company. Do you want to do that together with me? And he said yes, and he sold his company, and 1 week later, we started Zama. And so Zama started pre-pandemic. Actually, the first offices that we got them on the Monday. On the Friday, we would leave for a 3-month lockdown. So it was kind of crazy, but this is how things go in a pandemic. And it's been fantastic ever since. What we're doing basically at Zama is to make fully homomorphic encryption a reality. FHE has been a dream for cryptographers for decades. And it's now becoming a reality and a practical one. So a lot of people are still in their mindset focused on how things were 5 years ago. And so they think FHE is not ready for prime time, but they're wrong. And basically what we do at Zama is to prove them wrong by making FHE easy to use, efficient, and to work on the global adoption of FHE in every vertical, every market segment where it makes sense to actually use FHE, and it solves a lot of problems very elegantly and very efficiently.
One thing I like to say is whenever I say FHE to people, they say, oh, FHE is 20 years away, and my response is, well, people started saying that 20 years ago, and at some point, they have to be wrong.
Right. Yeah, absolutely.
Cool, guys. Let's next kind of get into, well, Pascal, I'd love to just share a little bit more about your background. You've been working in cryptography for a long time, and you gave a very humble introduction to yourself. But can you share with folks some of the work you've pioneered in cryptography over the years?
Oh, wow. So I carried out my PhD. I defended it in 1999, so it's been 25 years ago. At the time, if you can believe it, I was already working on homomorphic encryption. I was doing a PhD both, in France. We have this French guy here, based in Paris. So in France, we have this system for PhDs where you can spend half of your time in academia, half of your time in the industry. So I was doing that because it particularly makes sense for like computer science and for cryptography in particular. So on the industry side, I was working in the smart card industry, but I was like fascinated by the idea of homomorphic encryption. And at the time, there were already a number of mechanisms that were known to do homomorphic encryption, but they were like uneasy and they were like non-perfect and they had like either security issues or they were not like great. And so I worked on that in my PhD. I was lucky enough, I don't know, it's research, you know, it's very random, it's a stochastic process. You find stuff or you don't. And I happened to, at the time, be able to like repair like the most prominent scheme. At the time it was like Okamoto Uchiyama, which had a security problem, a security issue. So I kind of solved that, and that became the Paillier homomorphic encryption scheme. Woo. And it
You can
remained,
Google it.
It remained the gold standard of homomorphic encryption, I think, for a decade after that, like up until the point in 2009 where Craig Gentry, who was at IBM at the time, found the first instantiation of something that even I would think it wasn't possible to achieve technically, which was fully homomorphic encryption. Because homomorphic encryption was about you encrypted data, and then you're capable of doing operations on that encrypted data without decrypting it, right? And so at my time, if you can believe it, the challenge was to make addition clean. And now with fully homomorphic encryption is you can make addition and multiplication, therefore you can do everything that is Turing complete, you can process homomorphically over encrypted data and apply any function of your liking. So that was a dream for like decades, almost 50 years. And so it wasn't known to be even achievable at the time I was working on my PhD. And then in 2009, Gentry discovered like this first example of a cryptographic construction. Okay, it was like stupidly slow and so on. But it was answering the very question of existence. Are these cryptographic objects, you know, a dream, you know, a holy grail, unreachable, or is it actually a scientific reality? And he answered that question, and at the time you could just like encrypt bits and do like Boolean gates on bits, on encrypted bits. It would take 30 minutes to do one Boolean gate. But the question was not practical at the time. It was just, you know, this question of existence. And since a lot of cryptographers have opened their eyes on this and rediscovered the field, including myself, because I was very pessimistic about the existence of FHE, so I revised that judgment at that time. And now we've all, as a community, have been working on improving, you know, Gentry's approach and the bootstrapping and, you know, all these concepts that evolve around how you make FHE like practical. And we've come such a long way, orders of magnitude, and now it's like more efficient than ever. We still are missing like 3 orders of magnitude to make it as fast as plain text standard like normal computing, but we're getting there with hardware acceleration, which is coming by 2024, 2025-ish.
We'll come back to the hardware stuff.
Yeah, absolutely.
Only 1,000x to go.
Yeah, so that was like my personal contribution was to, in the early days of homomorphic encryption, to do proper homomorphic addition, but we can do so much more now.
Great. So Pascal Zama builds a lot of the core FHE math and cryptography. Guy Phenix is building a blockchain. How do Phenix and Zama work together? Guy, if you want to take it.
Yeah, so first of all, just to emphasize how big of a transformation FHE brings into the space. So what we're doing at Phenix is we're actually taking the FHE stack that Pascal and Zama provides and build a blockchain on top of that. And the reason we feel it's transformational and it's a good fit for blockchain is because there's been an inherent problem in the blockchain space from the first days of it, which is all the data on the blockchain is transparent. I'm pretty sure everybody here knows that. There is a lack of data confidentiality in blockchain. And there's been several efforts trying to solve that, trying to introduce solutions that are either using trusted execution environment or zero knowledge, and we may talk a little bit about that in a minute. But none of them has really solved and really brought up a platform that enables the Web2 entities and the people in Web3 that want to see this technology mature. None of the platforms really brought up a good solution. And the fact that we're able to utilize FHE now, the fact that FHE is mature and can be used to bring on-chain data confidentiality is quite transformational. It's really a missing piece here, because I think you mentioned earlier that blockchain, they do an amazing job in providing ownership of users. But what blockchain can do today is really provide you the ability to control who can see your data. And the introduction of FHE with Zama and Phenix would now enable users to not just prove that they own their data, but also to control who can see their data.
Right, so there's been a lot of people trying to do confidentiality on-chain. I guess Zcash was kind of the first real attempt in 2016, and there's a bunch of teams trying different approaches now. Why is the Zama Phenix approach interesting, and what does it enable that the other approaches cannot?
Yeah, okay, I'll start. So first of all, I know you mentioned Zcash. There is one thing that may be worth mentioning already in the beginning. Some of you have heard of Tornado Cash and may think, what is the difference there? So let's just make sure that it's very clear. The work that the guys at Tornado Cash did was to actually hide the identity of who does transactions. And that's the method of you don't know who transfers the asset from. We're not in that space. In our case, the transaction, the identity of who does the transaction is very clear. It's known. The content of the transaction, the asset is really what we're focusing on encrypting. Think of it as like HTTPS in that respect, which is a basic capability. Now, to the question that you brought up about how does FHE different from the other technologies. So if we take an example of zero knowledge, I think everybody here heard about zero knowledge. We all know that they're doing tremendous for scaling blockchain. But what zero knowledge can't really offer is complete confidentiality into the blockchain space. And the reason is that the way zero knowledge operate is that there is a third entity, it's a prover. The prover can always see the data. So zero knowledge are being forced to be fit to introduce encryption into blockchain, just because up until now, there wasn't really a good solution. With FHE, we're taking a totally different approach. The fact that FHE enables you to do computation on data while it's encrypted gives us the ability to finally, for the first time, bring on-chain encryption. So if you think of use cases like trustless games, on-chain poker, or on-chain blockchain, if you think about use cases like private voting, that would need encryption to be actually reality. And there are many more that we can probably talk about them in a minute. So that's in a nutshell where FHE is different from, first of all, Tornado Cash, as well as the zero-knowledge alternatives.
Yeah, fully agree. Zero-knowledge and FHE are like different crypto technologies. So with zero-knowledge, you can have some data, and without showing it, you can prove to somebody else properties of that data. But it doesn't allow you to do the same thing as FHE, which is I encrypt my data, I put it on chain. It's going to evolve over time, but it's fine because it's encrypted. So nobody is capable of revealing what's in the encryption box, in the encryption bubble. Only me. I mean, I'm the only entity who's capable of doing that by using like the private key. But we're also capable of having this data, evolving over time and computed over aggregated with other data and so on and so forth. And ZK does not allow that. Probably what's going to happen in the future is some more integration between FHE and ZK, because ZK is very powerful cryptographically. We can prove that a computation was correct, for instance. I can delegate a computation. I don't have to redo it all over again. You can just, as a prover, issue a proof, and I can verify super quickly that you indeed computed this correctly. FHE is not capable of doing that. So both are different. They bring something different on the table. At some point, what we can expect is some more integration between the two techniques, especially in the world of blockchain where things are maximally adversarial. And we probably need data confidentiality associated with the power of computational verifiability brought forward by ZK. So in the future, it's probably going to be like integrated, both solutions.
So Pascal, you all have launched recently an FHE EVM thing, and Guy, y'all I think are working with that to build Phenix. Can you all talk a little bit about the developer experience today on kind of this first thing that's coming out? What tools work, what tools don't work, how do developers copy existing code, whatever else?
Yeah, it's a great question. So we always feel that working on blockchain can become complex. Our goal, coming from a very practical approach, was to make it as seamless as possible for the blockchain community to introduce encryption. So we're utilizing an FHEVM based on the Zama stack. And what it basically means is if you're a Solidity developer, if you develop your smart contracts for Ethereum, there is really very little difference between using your existing Solidity contract and then running them on Phenix. The only thing that's different is that there is an additional library that you would need to use to encrypt the data that you want to encrypt. But other than that, it's pretty much the same. So the transition from existing Ethereum Solidity-based contract to Phenix-based contract is very, very easy. You don't need to learn a new language. You don't need to be a cryptographic expert to that respect. It's a very practical approach.
Yeah, everything we do as Zama is basically to make FHE, which is very complex technology. So it's super hard to use. Basically, you need to have like a PhD in crypto to be able like to build homomorphic applications. And there's also an efficiency problem compared to what you do naively, like in the plain text operations. Homomorphic operations are costlier. But what we're trying to do at Zama is to abstract away all this complexity, to make it disappear, to provide the tooling, it could be homomorphic compilers, homomorphic virtual machines and everything, to the developers community, so that they can instrument and use FHE without all this like background that currently you need when you want to build a homomorphic application. So we want all this to disappear, and as Guy was describing, basically for FHEVM, it's the EVM augmented with homomorphic capabilities. So suddenly in Solidity, the developer's experience is exactly the same. We just expose new data types, encrypted integers, and basically operations on these encrypted integers, and boom, and there you have. The developer doesn't need to know all the gory details about how it works under the hood to be able to use their natural creativity and build these new experiences and address these new use cases where privacy is really needed. And as we were saying at the very beginning, data confidentiality was the big missing piece in the blockchain world. So we think FHEVM is going to be somewhat of a revolution within the revolution. Like in the blockchain space, there will be. I think now is the time where we're transitioning to a world where things are going to be private by design, and not just by law or anything. But you can enforce data confidentiality with cryptographic strength, and this is going to be transformative for the blockchain space, but also outside of it, like for other applications like machine learning, where you do like homomorphic inference. There are plenty of encrypted databases. You can think of plenty of different use cases where FHE is going to be disruptive as a technology.
Yeah, and maybe just to add one thing, we have a DevNet that's started in July, limited access, and we did a couple of hackathons over that DevNet. And we were overwhelmed with developers' ability to bring really viable solutions in a matter of a couple of hours. We had teams participating that said that they were able to develop private voting applications in 24 hours in one of the hackathon, while they were trying to do the same using ZK for over several months and weren't even able to get to what they were able to do in 24 hours. It's really FHE is really the right tool and the missing piece here.
Yeah, we were discussing backstage this framed, implementation. So they implemented the Mafia game. Do you know that game, Mafia? But fully with FHE, fully on chain. And so it's amazing to see that gaming could be an application of FHE. But yeah, of course. I mean, when you do games, you need to hide your hand or whatever, if it's poker or whatever else. And so it makes sense. And the game was actually developed over a weekend. Yeah. I think it speaks volumes to how successful we've been, like trying to, hide all this complexity and have a way for developers to just use their creativity and not care about all these details about how it works under the hood.
Well, yeah, one of the things we were always concerned about when we were investing in Phenix and working with the Zama guys is it's too early, and obviously you never know, but one thing that gave us a lot of confidence was understanding that, hey, they can port the EVM into this, expose a few new opcodes, and otherwise you can copy-paste existing code over and run at reasonable performance. And the fact that you can make it that easy was really a big signal to us that, like, hey, it was clearly 20 years ago, it was too early, maybe now is finally the right time to make the jump. So that was a big signal for us. Speaking of the EVM performance, what can we expect with Phenix and today with general purpose compute, and then maybe tomorrow with some acceleration?
You want to start?
Oh, wow.
And for context, the EVM today runs at 1520 TPS, kind of roughly on ETH-L1.
Yeah, there are plenty of ways how, I'm the CTO of Zama, so I'm a lab rat. I'm basically, so sometimes the people, I come on stage and talk about what we're doing, but basically I'm more on the, working with the teams on how to improve things. So we're seeing like big changes happening over time. To make basically the FHEVM faster, because basically we have to support 32-bit arithmetics, 64-bit arithmetic. So for those of you who are not familiar with it, but the EVM works on native 256-bit integers, except that in most of applications, developers usually need like 32-bit integers, 64-bit integers for like 99% of use cases. But we're trying to be like fully compatible. So there's still like, right now, we're not supporting 256-bit integers for real. But so if we want to achieve like full compatibility with the EVM, we have to go there. There are plenty of ways how to implement these arithmetic operations. So right now we're trying to optimize and to like improve the performances of that. Also, there is a threshold decryption part that we're improving over time, which is also part of the FHEVM stack, which is a really important ingredient. And in the future, more long term, there is like I was speaking about integrating ZK with FHE, which is doing provably correct FHE computations. Right now, a validator does the FHE computation, and that at some point, there is a consensus between all the validators that redo the same FHE computation. That's good enough right now to start with, with FHEVM, but at some point, we will be able to have one validator do all the heavy lifting and generate a proof that is like, verified in a fraction of a second by the other validators, and they can validate that the computation was correct. This is coming on more, it's more of a long-term thing.
And maybe addressing the hardware question, I think today there are over a dozen of companies that are actually looking to build hardware acceleration for FHE. Intel just announced last week its plan to release a hardware accelerator for FHE. There are several companies that are looking into that. So it does feel that in the next 12 to 18 months, I know some are even claiming in 2024, but I would say, realistically, 12 to 18 months, we're going to see dedicated hardware being built and released for FHE, which is going to make a transformational change in the performance. I think it's worth mentioning that one of the key differences between FHE and ZK is that ZK, great technology, but really very successful only in the blockchain space. I think the FHE potential starts with blockchain, but way broader than that. And that is why we see a lot of companies looking into building hardware acceleration for that. So we're really like the first ones in that space, and we're going to see quite a lot more coming up.
Let's get into, I guess, actually a little bit, good lead point, Guy. Can you all talk a little bit about what are some opportunities you see for FHE, even beyond blockchains? You all both kind of alluded to it, but where can we hope to see this in a couple of years once the performance gap is closed?
Yeah, so maybe I'll start with some of the use cases that we see at Phenix, and I'll probably let Pascal talk about the work outside of Phenix. But what we feel in the short term, use cases that we're planning to target is using Phenix and the FHE capabilities to introduce private voting for DAOs, which is a capability that just cannot happen without the ability to encrypt the voting. Another application is trustless games and on-chain games. We talked about a few that were developed, but there is actually quite a lot of demand for on-chain games like poker. And again, you cannot really do on-chain games if everybody can see the content of your hand. And then there is, of course, the third pillar of account abstraction. We all heard about account abstraction, the ability to put a private key on a contract and use that to sign transaction. And that actually removes a lot of the barriers that people have today. With Phenix, it's very trivial because that's exactly what we're doing. We're providing the ability to put any type of data, including your key, and actually use that to sign transactions. So that for me is like the short-term use cases to start with, and of course scale beyond that. I will add that there is a huge potential outside of that. And for me, it goes, first of all, and pulling in the Web2 entities, the corporates of the world, the financial institute of the world, that I just don't see a way to them today to move from Web2 to Web3 if we can't give them the option to provide their data in a confident way. It has to be, it's like a basic capability. So I feel that pulling in the corporates and the financial institutes into Web3 requires encryption. And then, of course, you've also alluded to machine learning algorithms, where you want to have the ability to put data on-chain, because we all understand that the machine learning models are as good as the data that they're used to be trained on. How do we use the data? How do we pull that data and we put it encrypted so it can be used for training? Distributed model is another use case.
Absolutely, which is still, by the way, we know how to do machine learning inference homomorphically in the Zama stack. So nothing to do with the FHEVM, but so basically we're not a blockchain company. Zama is a cryptography company. We want to be a technology enabler for FHE, whatever the domains. And so in machine learning, there is a lot of appetite for, people, I don't know if you've seen, but in Italy, like they forbid, I think that it's different now, but they forbid the use of ChatGPT in Italy because of the data privacy issues. So the dream here is to be able to apply FHE to that kind of scenarios where you encrypt your data, you send that to the cloud, and it's basically processed by a machine learning model, but homomorphically, and then suddenly the answer comes back to you encrypted, you decrypt it, and you get exactly the same result. So what we want to provide, what we're working on, what we're providing, everything we do is open source, so you can just download our stuff from GitHub, is a way for machine learning scientists to take a model that is pre-trained, push the button because it works with the compiler, no need for a cryptographer or any knowledge, and that gives you like a homomorphic application that you can deploy directly in the cloud that does, which is a homomorphic equivalent of that model. So it does exactly the same thing, only it takes as input encrypted data, outputs encrypted data. So the thing that people are dreaming about is to be able to do the training, building the model on encrypted data. And that where it's, right now it's not like, well, everything you can compute homomorphically, but if we look at performance issues, it doesn't make any sense right now.
Right.
But I have no doubt that there will be a solution in the future, and that's like terribly exciting.
Yeah, so we're wrapping things up, but yeah, we're just to stay where things are. You know, the hardware acceleration's coming. Pascal earlier said we got 1,000x to go to get the plain text performance, but the hardware is going to cut in the next 12 months or so, maybe 18. And when that happens, I think this whole space is just going to blow up in a big way. So we're very excited to be here early, be part of it, getting to work with two amazing teams. So thank you, Guy. Thank you, Pascal, for being here. And with that, I believe lunch is served outside in the foyer. So thank you all, and we'll be back here in an hour, I believe.